Section 3.2, Raleigh's theorem and the mean value theorem. Look at all those stars. That means it's very, very important. Recall, the extreme value theorem said that a continuous function on a closed interval must have a maximum and a minimum on the interval, and it can also happen at endpoints. So what happens if at the A and the B, the endpoints of an interval, my y values are equal? Well, that would mean if that's the case, then there is at least one number C in the open interval from A to B such that f prime of C is 0. So there's at least one horizontal tangent. Now this is actually a special case of the mean value theorem, which we're going to be learning about today. So if I just connected these 2 points, obviously at every point in the open interval from A to B, the slope is 0. But I also could be looking at something like this. And now you can see I have at least 2 places in the open interval where I have a horizontal tangent. And that's what Raleigh's theorem says. It's a special case of the mean value theorem. It says if my y values at the endpoints are equal, then there has to be at least one place in the open interval from A to B where the derivative at that place is 0. So let's just look at a couple of examples. Okay, I'm going to freeze the frame. There's problem 1. You might want to freeze it and write it down. Here's problem 2. You might want to freeze it and write it down. Here's problem 3. Also, here are a list of symbols. You might want to know mathematical symbols. They're recognized universally around the world. So you might want to know those. They are used in your college classes. Examples. Determine whether Raleigh's theorem can be applied to f on the interval. Then, if so, find all c values such that f prime at c equals 0. So Raleigh's theorem states that the function must be continuous on the closed interval and differentiable on the open interval. That is the conditions that must exist before you can apply the rest of the theorem. So here we have a polynomial function. It is continuous on the closed interval because polynomial functions are, and they're also smooth, and so they are differentiable on the open interval. So we've met that first condition. Now we need to show f at A equal to f at B. F at 1 is 0, f at 2 is 0, so now we've met that condition. Then there has to be at least one place where the derivative is 0. So since f at 1 equals f at 2, and f of x is continuous, then f prime at c has to exist. So here is f prime, and that is equal to 0 when x is 3/2. So f prime at 3/2 is 0. Notice that 3/2 is on the open interval from 1 to 2, which is where we have to be. Now let us consider the same function, but on the closed interval from 0 to 3. So f at 0 equals 2, f at 3 equals 2. Since our function is continuous, there has to be a c on the open interval where the derivative is 0. And we know that at 3/2, that is between 0 and 3, so we again have that situation. X is the line y equals x. X to the 1/3 is this function. Both are continuous. You had your rules of continuity that said when you added 2 continuous functions, you still have a continuous function. So our function is continuous and differentiable on the interval from 0 to 1. So now we're going to find f at 0, f at 1. So the derivative has to equal 0 somewhere from 0 to 1. That is what Raleigh's theorem says. Setting my derivative equals 0 allows me to do this algebra and multiply by 3. And I want to solve for x. X is being raised to the negative 2/3. So I want to remember that that is 1 over x to the 2/3. 3 over 1 equals 1 over x to the 2/3. Really neat thing is we can take these fractions. If this equals this, I can reciprocate them, and they are also equal. So I have 1/3 is equal to x to the 2/3. Again, we're solving for x. So I need to raise this side to the 3/2 to get the x isolated. So now we're going to raise this side to the 3/2. Now, this side to the 3/2, a way to think about this is cubing the 1/3 and then taking the square root of it. Now, if we think about x squared is 1 over 27, the square root is plus or minus, because it's an equation, 1 over 27 under the radical. Square root of 1 is 1. Square root of 27 is 3 square roots of 3. So we have plus minus 1 over 3 square roots of 3. Now, let us remember, if I go back to this problem here, the derivative is undefined when x is 0. But if we go to the original problem, x equals 0 is not on the open interval. So my function is differentiable on the open interval. We actually have a vertical tangent. So finishing out this problem, we have x is plus or minus 1 over 3 square root of 3, but let us recall we need it to be on the open interval from 0 to 1, so we have to throw out the negative solution, and it is only this solution. Again, Raleigh's theorem says let f be continuous on the closed interval from a to b and differentiable on the open interval. Cosine is always continuous. We know what it looks like. So it is certainly continuous on the closed interval. So cosine of x is continuous, and we know that f prime of c, the derivative of cosine, is negative sine of x, and negative sine is still continuous on the open interval from 0 to 2 pi. So f at 0 is cosine of 0, 1. F at 2 pi, cosine of 2 pi is 1, so these are equal. So now we can continue with Raleigh's theorem, finding the derivative of cosine, setting it equal to 0. So negative sine of x equals 0 is the same thing as sine of x equals 0, so I need the angle whose sine is 0. That's going to happen at 0, pi, 2 pi. If you think your unit circle, every place where the y-coordinate is 0. But we want to be on the open interval, and the only one on the open interval is pi. Okay? There has to exist some c such that f prime at c equals 0 on the open interval. So you got to be careful. So just as a reminder, remember that f prime is 0 when the numerator is 0 and denominator does not equal 0. All right, our main theorem, and this is a big one, it shows up for the whole rest of the year, so you really need to know it. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Hey, that sounds a lot like Raleigh's theorem. Well, remember, Raleigh's theorem is a special case of the mean value theorem. Then there exists a number c such that f prime at c, or the instantaneous rate of change, or the slope of the tangent line at c, is equal to f of b minus f of a over b minus a, which is the average rate of change, which is the line connecting the endpoints of the secant. Does that look familiar? It should. This is one of the most important theorems of calculus, and it's very closely related to the fundamental theorem of calculus. It guarantees the existence of a tangent line that is parallel to the secant line through some point A, F at A, and B, F at B. Very, very important theorem. Example 4. Apply the mean value theorem and find C such that the derivative at C is equal to the slope of the secant. So my problem is this. The function is x times x squared minus x minus 2, which we recognize this as a polynomial function. We distribute that x, and we're on the closed interval from -1 to 1. Since it's a polynomial function, f is continuous on the closed interval, and f is differentiable on the open interval. Therefore, there has to exist some derivative at c on my function that has the same slope as the slope of the secant. So we need to find f of b and f of a. So f at 1, substitute 1 in, is -2. And f at -1, substitute -1, and we get 0. Okay? So my f at b minus f at a over b minus a is f of 1 minus f of -1 over 1 minus -1. So we have -2 minus 0 over 2, which is -1, and that is our average rate of change. So now what we're going to want to do is to note that we are going to find where the instantaneous rate of change is equal to -1, and we're going to do proper algebra. So here is our function f of x. There's the derivative, and we want the derivative to equal -1. Here's my instantaneous rate of change equaling my average rate of change. Remember that when you are solving an equation of this type, we need to set it equal to 0 and then factor it. This factors very nicely, and my values that solve the equation are -1/3 and 1. But now we need to go back and we need to only answer with the solution that is in the interval. So my closed interval is -1 to 1. The C that is on the open interval from -1 to 1 does not include where x is 1. So the only solution is when x is -1/3. The slope of the tangent line is going to be equal to the slope of the secant line. Only happens at x equals -1/3 in that interval. Your TPs for this section are 3, 9, 11, and 39. See you next time.